we denote the complexity of an algorithm as O of f of n, where constant factors and lower order terms are omitted from f of n. So, for example, take an sorting algorithm where we are given an array of numbers and we need to sort the numbers in an increasing order. Now, if the array is already sorted, my algorithm may not need to perform any operations. Or if the array is half sorted, then the algorithm might need to perform some number of operations. And if the array is in the reverse order, then it might need to perform more number of operations. So what the big O notation does is it considers the worst case and it gives us the maximum number of operations that our algorithm might have to perform. That is how it gives us an upper bound to the number of operations that our algorithm has to perform. Now let's take a look at what are the calculation rules. How do we actually calculate big O of n for any given algorithm? Now, if our code now in the code snippet over here, you can see that we declare two variables A and B and we initialize them to values 10 and 45. And then we declare another variable C, which is the sum of A and B. If our code consists of a finite number of operations, like in this case, then we'll say that the worst case time complexity of our algorithm is big O of 1, or we'll say that it has a constant time complexity. Moving ahead. Now, what about if we have a loop? So the time complexity of a loop will estimate the number of operations that the loop performs. For example, this first loop over here, we can see that this loop will iterate n number of times because we first initialize I to 1, we are incrementing it by 1 every time, and it has to reach n. And we'll assume here that this code within the loop has a time complexity of big O of 1. Or basically, there are some finite number of operations within this code which are independent of the input size n. So then the overall time complexity of this loop will be big O of n. Let's come to the next example. Over here, we can see that I is again starting from 1, is incremented by 1 in each iteration, and it has to reach 3n. Now, if it has to reach 3n, then the actual number of times that this loop will iterate will be 3n. But as we saw, that the constant multipliers and lower order terms are removed while calculating the worst time complexity or in the big O notation. So that is why we'll say that the time complexity of this loop is also big O of n only and not big O of 3n. So the important lesson over here is that constant multipliers and lower order terms are removed while calculating the big O time complexity. Now here are some examples. You can try out what you learned just now and try to figure out what is the time complexity of these two codes. Now let's see the answers to these problems. Now the worst case time complexity of the first code is big O of n because I starts from 1 and it increases by 2 in each iteration and it has to go till n. So the actual number of times that this loop will execute is actually n by 2. But as we remove the constant multipliers, so the time complexity of this first code will be big O of n. In the second example, we have two loops. The outer loop we can see will be executing n number of times and the inner loop will also be executing a number of times. So in each iteration of the outer loop, the for loop within the second for loop will execute n times. So the total time complexity becomes O of n times n, that is O of n square. So the rules that we learned till now is that we have to neglect the constant multipliers and lower order terms in the expression f of n that comes with O, with the big O notation. I'll see if there are any doubts. Right. Let's move forward. So now what we see here is a comparison of different orders of time complexities. So this is a constant time complex. Big O of 1 represents a constant time complexity. That is, the algorithm will always perform some certain finite number of operations which are independent of the input size n. Then the logarithmic time complexity has a higher order than the constant time complexity. And big O of n has even higher order than this. The time complexities O of n square and 2 of n have even higher orders. Now, why do we need to see this? This is because when these will be in addition, we need to omit the lower order terms. For example, you calculate for some algorithm and you get f of n within the big O notation as n square plus log n. Then we will not write that the time complexity of the algorithm is O of n square plus log n. But because log n is a lower order term than n square, so we'll omit log n. And the overall time complexity of that algorithm will only be O of n square. So we need to know what are the orders of these terms and how they compare with each other to calculate the overall time complexities of various algorithms. Now, here are some more examples. You can scan this QR code and so in the third example, you can start by observing that in each iteration of the outer loop, how many times will the inner loop execute? In the outer loop, I starts from 1 and has to go till n and is incremented by 1 in each iteration. So it will obviously execute n number of times. But how much times will the inner loop will be executed in each iteration? For the fourth example, you can see that I again starts from 1 and it is multiplied by 2 in every iteration and it has to reach n. So what we need to find is basically how many number of times 1 needs to be multiplied by 2 in order to reach n. Are the third and fourth examples visible to everyone right now? Am I audible? Did everyone go through the first and second examples? Okay, I'll start from the first two examples again. We'll go a little bit fast because this was already covered. Is everyone on calculation rules right now? Okay, let's start. Right. So the first rule is that if we have a finite number of operations which are independent of the input size n, then it is said to have a constant time complexity or big O of 1. For example, in the code snippet over here, we are declaring two integers a and b, and we are initializing them to 10 and 45. Then we are declaring another integer c and initializing it to a plus b. Now, here only we are performing three operations, which is independent of the input size n. So this is has a constant time complexity or big O of 1. Moving forward, now what do we do if we have loops? For loops also, the time complexity basically estimates the number of operations that the loop performs. So in this first example over here, I starts from 1 and it has to go till n and it is incremented by 1 in each iteration. So the code within will be executed n number of times. And we assume over here that the code within the loop has a constant time complexity or it has some constant number of operations, which is independent of the input size n. Then the overall time complexity of this loop will be said to be big O of n. Now in the second example over here, we have I starting from 1 and going till 3n, and it is incremented by 1 in each iteration. Now you might say that the actual number of times that this loop will be executed will be 3n. So the time complexity of this loop becomes big O of 3n, but that is not true. Because what we do here is that the constant multipliers and lower order terms are removed while in the big O notation. So the overall time complexity of the second example will also be big O of n only and not big O of 3n. Is everyone up with this? Right. Let's move ahead. So now you can check yourself out. Calculate the time complexities of these two examples over here. Remember, the rules are that the constant factors and lower order terms are removed. I'll wait for a couple of moments. Let's see what are the answers. So for the first example, we can see that I starts from 1, it has to reach till n, and it is incremented by 2 in each iteration. So the actual number of times that the loop will iterate will be n by 2. But as we have to remove the constant multipliers, the answer will be big O of n. In the second example, we can see that there are two for loops. The outer for loop will run n times. And in each iteration of the outer for loop, the inner for loop will also run n times. So the overall time complexity becomes big O of n times n, or big O of n square. Moving ahead, here we see a comparison of different orders of worst case time complexities. So basically, the lowest order is of constant time complexity, that is big O of 1, where we have a finite number of operations which are independent of the input size. Then comes the logarithmic time complexity, big O of log n. Then comes when we have a time complexity of n, and the time complexity is n square and 2 to the power n have even more higher order than these. Now, why do we actually need to know the orders of these time complexities? That is because when these are in addition, then we will have to omit the lower order terms. For example, in some algorithm, we find that the function f of n over here is of the form n square plus log n. Then the overall time complexity will not be O of n square plus log n. But because log n has a lower order than n square, so we'll have to omit it. And the overall time complexity will only be big O of n square. So we need to know how these different time complexities compare with each other to calculate the worst case time complexity. Here are some more examples. You can scan this QR code and mark your answers. Can everyone see the QR code now? Right. I'll wait for another minute for everyone to calculate and mark their answers. For the fourth example, there seems to be some confusion between O of n and O of log n. Pay attention here clearly. It is not I equals I plus 2, but it is I equals I times 2. Right, let's go to the answers. So in the third example, we see that the outer loop is going to iterate n number of times. And in the inner loop, j starts from 1 and goes till n, increasing by 1 every time. So first j will start from 1 and go till n. So the inner loop will execute n times. When I equals 2, j will start from 2 and go till n. So it will execute n minus 1 times. When I equals 3, j will start from 3 and will go till n. So it will execute n minus 2 times. So this way the inner loop will be executed n plus n minus 1 plus n minus 2 plus 2 plus 1, these many number of times, which is equal to n times n plus 1 by 2 or n square plus n by 2. But if you remember, we have to omit the lower order terms and the constant multipliers. So we'll remove this n over here and we'll also remove the by 2. So the overall time complexity for the third example will be big O of n square. Coming to the fourth example, we start from I equals 1 and I has to reach till n, and it will be multiplied by 2 every time. So what we need to calculate over here is how many times 1 needs to be multiplied by 2 in order to reach n, which is basically n only to the log n to the base 2. All are not working only. Okay. Is everyone with me till here? Yeah, I'm trying. Yeah, it's not. Nothing is there. Only one window is there. Hmm. Yeah, it's showing white screen there. I think it's showing white screen. Once again. Let me check in the third example, I goes from 1 to n and it increases by 1 every time. Yeah, yeah. Now when I equals 1 goes from, j has to go from 1 to n. So it will execute n number of times. When I equals 2, j has to go from 2 to n. So it will execute n minus 1 number of times. When I equals 3, j will go from 3 to n. That is, it will execute n minus 2 number of times. This way, the total number of times that this code will be executed will be n plus n minus 1 plus n minus 2 plus n minus 3 plus 2 plus 1, these many number of times. And we know that the sum from 1 to n is n times n plus 1 by 2 square plus n by 2. But as we have to omit the lower order terms, we'll omit this n. We also have to omit constant multipliers, so we'll remove this 2. And the overall time complexity will be big O of n square. For the fourth example, I will go from 1 to n and it will be multiplied by 2 in each iteration. So what we need to calculate is how many times 2 needs to be multiplied to 1, incrementing by 1. When I is 2, j has to go from 1 to n, but it will be incremented by 2 in each iteration. So in that case, the inner loop will run n plus 1 by 2, the greatest integer factor of these, many number of times. When I becomes 3, j has to go
I
from
changed.
1 to
It's still on the screen.
n, and it will be incremented by 3 in each iteration. So the inner loop will run n plus 2 by
As per
3,
Soros,
the
he's saying
greatest
that
integer
if I
function
keep
of
the
that
cursor on
number
the
of
screen, then
times.
it's a problem.
Now
But
we do
I'm
not need to
changing, no?
calculate the exact number of times that the loop runs, but we have to give an approximate value of that. So the total number of times that the code will be executed will be n plus n by 2 plus n by 3 till n by n. N by n becomes when I is n.
It is visible
Now
now.
you can take n common from all of this. Then what you'll get is 1 plus 1 by 2 plus 1 by 3 plus 1 by 4 till 1 by n. And we know from integration that this can be approximated as the integral of 1 by x dx, which will give us ln n. Therefore, the final answer will be n times log n.
Oh, now is it visible, right? Oh, I think I opened what I was doing was I opened on the tab and I am like Arya was messaging it. I was messaging in that phone, messaging in that tab. Uh, then cursor was there on that tab, so this was coming widescreen. I think.
Is everyone with me till here?
Okay, I'll do that. I'll keep the cursor right there. Is it now visible yet? Still, it's visible, no? Yeah. Okay. I'll log in my phone then using programming club man. Then I should answer there, no? Yeah.
Did everyone understand this example, or do I need to explain it once more? Right. So in the sixth example, what we see is when I is 1, j has to go from 1 to n, and it will be incremented by 1 every time. So naturally, this loop will run n number of times. When I equals 2, j will go from 1 to n, but it will be incremented by 2 every time. So the inner loop will run n by 2 number of times approximately. When I equals 3, j has to go from 1 to n again, but it will be incremented by 3 every time. So the inner loop will be executed n by 3 times approximately. So if we follow this pattern, you can see that the total number of times that the inner loop will be executed will be n plus n by 2 plus n by 3 till n by n. Now we can take n common out of this so that what we are left with is 1 plus 1 by 2 plus 1 by 3 till 1 by n. And from basic integration, we can say that this is approximately integration of 1 by x dx, which is equal to ln n, that is base power e. So the final answer will be n times log n. This over here is the greatest integer function. So this is the exact number of times that the inner loop will be executed. That is n plus 1 by 2 GIF of that. But we do not need to calculate the exact number of times. We have to calculate an approximate value of that. So we can directly take n plus n by 2 plus n by 3. Moving ahead, we'll see an application of this. That is, we'll go through a searching algorithm. What we want to do now is that we want to build an algorithm to search for a given number in a given array and return whether it is present in the array or not. So here we see that we have an array that consists of some numbers. We calculate n as the size of the array by the size of the first element of the array. So the size of array of 0. What is array of 0? Array of 0 is 3, which is an integer. And integers are stored in 4 bytes. So size of array is basically the number of elements of the array times 4 bytes. So integer n equals size of array by size of array of 0 will give us the number of elements in the array. Then we here declare and initialize a variable x with the value of 47, and we want to check whether this number is present in the given array or not. Size of array is basically the number of elements of the array. So we write a for loop for this. Now this here is a linear search. So what we do in linear search is that we go then we here declare and initialize a variable x with the x of the array is 0, and we go till n, till I is less than n. That is the size of the array. And in each iteration of the loop, we check if the element of the array is equal to the number we are looking for. If it is, then we print that we have found the number and the index we have found it at. And we this break keyword is used to break through the for loop. So if the algorithm finds that the element of the array is equal to x, it will now this here is a linear search. So when we do a linear search is that we looking for find the value at any index, then I will be incremented to the last value, that is I will become equal to n. So we check if I is equal to n, that is if we did not find the number at any position. If that's the case, then the element was not present in the array, and so we print that the element was not present in the array. So this is linear search, and in linear search, we have to go through all the elements of the array. So you can say that the time complexity of this algorithm is big O of n. Am I audible now? Is it clear? Okay, I'll go through the linear search again. So what we want to do is we want to build an algorithm to search for a number in a given array. And first we will see what is linear search. So in linear search, we go through each element of the array one by one from the starting and check if that element of the array is equal to the number that we are searching for. So here we write a for loop which will go from the index 0 till n minus 1, and it will check if the array at that if the element of the array at that index is equal to the number that we are looking for. If it is, then we'll print that we have found the element at the index and will break out of the for loop. So for example, if we found the number at the index 6, then we'll break the loop when I is 6, and then I will not be incremented further. But if we did not Is the screen visible now? Right. So what we saw just now was linear search, where we go through each element of the array one by one from index 0 and check if the element of the array is equal to the number that we are looking for. So the time complexity of this is O of n, big O of n, because if the element that we are looking for is present at the last position, then we'll have to go through all the elements. So that is why the worst case time complexity, that is in the big O notation, it will be O of n. We have another algorithm for searching, which is the binary search. In binary search, basically we need the array to be sorted first, and then only we can use binary search. Here first, we check if the element at the middle of the array is greater than or equal to or smaller than the required number. Accordingly, then we change our input data, that is the numbers that we look at, to the first half of the array or the later half of the array. For example, if the middle number is greater than the number that we are looking for, then we'll take the input to be the first half of the array. If it is less than the number that we are looking for, then we'll take the input to be second half of the array. This way, we'll be reducing the input size by 2 every time. Here first, we check if the element at the middle of the array is greater than or equal to or smaller than the required number, binary search. Accordingly, then we change our input data, that is the numbers that we look at, to the first half of the array or the later. Because we are reducing our input size by 2 every time until we reach the last element, the worst case time complexity becomes the number of times we need to divide n by 2 to reach one element, that is big O of log n. Now let's see how it is implemented in code. Here we are writing a binary search function which will take input an array, the lower index, the higher index, and the integer that we are searching for. Is everyone with me? Right. So what we do in the binary search function is that while the starting index is less than the ending index, we calculate the middle index. We see if the array element at the middle index is equal to the number that we are looking for. If it is, then we have found the number, and so we return the index, that index. Then we see if the number is, if the element at the middle index is lesser than the number we are looking for. If it is less, then we have to shift our input to the second half of the array. So we'll set the starting index to be 1 plus the middle index. If both the first cases turn out to be false, that means the middle element of the array is greater than the number that we are looking for. So we need to shift our input to the first half of the array. So we'll set the ending index to be the middle index minus 1. Now, if we have performed the for loop and we were not able to find any element that matched x, that means the element was not present in the array, and that is when we'll go out of the while loop. If we ever find an element of the array which was equal to the number that we're looking for, then the return function over here will return that number and the function will end. If we did not ever find a number that we're looking for, then the while loop will end and we'll reach to the code over here. In which case we return -1 to indicate that the number that we are looking for was not present in the array. In the main function over here, we have an array. X is the number that we want to look for. Y is another number that we want to look for. We can see that X is 40, which is present in the array. Y is 44, which is not present in the array. Here we again calculate the size of the array. We use the binary search function that we wrote just over here to find the index at which the number that we are looking for will be present. Similarly, we do that. The result 1 will be the index for the number y. So what we see over here is that the binary search algorithm divides the input size by 2 in each iteration until we finally reach the element that we are looking for. So the worst case time complexity will be O of log n. Moving ahead, we'll look at some common time complexities that are frequently seen in competitive programming. So first is O of 1, that is the constant time complexity. So the running time of a constant time algorithm, which does not depend on the input size, will be big O of 1. And this will be a direct formula that calculates the answer. Then we come to the logarithmic time complexity. We had just seen an example of this, which is binary search. Usually a logarithmic algorithm halves the input size at each step, and which gives us this time complexity. Then algorithms which calculate the prime factorization of an integer by for checking the primality or compositeness of an integer naively out of the big O of square root of n time complexity. Then linear algorithms go through the input a constant number of times. And this is often the best possible time complexity because it is usually necessary to access each input element at least once before reporting the answer. So big O of n is often the best time complexity that you can get. Then the efficient sorting functions from the C++ standard library that you would have seen in the first lecture, the sort function in vectors. Those functions have a time complexity of O n log n. Another possibility for getting this time complexity is that the algorithm uses a data structure where each operation takes O of log n time. Moving ahead. Now, if we want to go through all the possible pairs of input elements, that is, for the first element, we have n choices, and for the second element also, we have n choices. Then our algorithm often contains two nested loops, each going through n, and which gives us a time complexity of O of n square. Instead, if we have to go through all possible triplets of the input elements, then we'll have a time complexity of O of n cube. So if we have to iterate through all subsets of size k of the input elements, we'll have a time complexity of O of n to the power k. Coming to the exponential time complexity, If we have to iterate through all the subsets of the input, then the time complexity becomes an exponential one, because the number of subsets of any set is 2 to the power n. And if we have to iterate through all of them, then we'll get a time complexity of O of 2 to the power n. Then the next time complexity we have is a factorial one. If we have to iterate through all the permutations of the input elements, then we get this time complexity. Is everyone with me or till here? Right. So here comes the QR code for the attendance. You can scan this and fill it to mark your attendance. I'll wait for a couple of moments. O of n factorial was if we have to iterate through all the permutations of the given number of elements. So the number of permutations of n elements is n factorial. And if you need to go through each of them, then the time complexity will be O of n factorial. Two to the n or exponential time complexity we get when we have to iterate through all the subsets of the given number of elements. If we have n elements, then the number of subsets of them is 2 to the power n. And if we have to iterate through all of them, then the time complexity will become O of n, 2 to the n. The time complexity will be O of n cube if we want to go through all the possible triplets of the input elements. So in a triplet, for the first element, you have n options. For the second element, you have n possibilities. For the third element, you again have n possibilities. So the total number of triplets is n cube. And if we want to go through each of them, then the time complexity will be O of n cube. Right, let's go ahead. So what is the maximum permitted complexity? Now, what we had seen was the number of operations that a computer can perform in a second are approximately 10 to the power 8. And we need a program to run within a certain time limit in CP.
Hello.
So there is a limit on the maximum time complexity that our algorithms can have, depending upon the input
Okay,
size
okay. I try
and the
calling her,
time
but if
given.
she doesn't leave, what should I do? Shall I mute her?
Usually the time limit
Okay, I'll
given
try her.
in contest problems is 1 second. And a smaller time complexity means that the code is more efficient. So if your input size is less than 100 or it is up to 100, then the maximum permitted complexity that your algorithm of the program that you're writing can be O of n to the power 4. Similarly, if the input size is up to 10 to the power 6, then you can have a maximum time complexity of O of n log n. You need to keep in mind the maximum permitted complexity that you can have for the given input size in order to write algorithms that will be accepted. We'll move ahead. So what we were talking until now was the worst case time complexity. So what is this best case and worst case? The best case basically refers to the most ideal case in an algorithm. It represents the scenario where the input data is already in the most favorable state, or when the algorithm encounters the most efficient case. The number of operations that the algorithm performs in such a case is denoted by this notation, the big omega of f of n notation. It gives the lower bound for the running of the algorithm or the minimum number of steps that the algorithm will take for any input. But in competitive programming problems, the best case time complexity is typically not emphasized and not learned about because it does not provide a complete understanding of the problem. It does not tell us how efficient our algorithm is. We need an algorithm that works in the worst case scenario. That is when the input is in such a way that our algorithm is compelled to perform all the possible operations it can. This is because the test cases in the competitions are designed to check whether the code is efficient and it works for the worst case inputs. So we study the worst case time complexities only. The worst case time complexity provides an upper bound on the algorithm's performance and allows us to ensure that solutions are efficient for a wide range of inputs. Right, we have come to the end of this topic. You can scan this QR code and mark your feedback. In most of the algorithms that you encounter in CP, the base is usually 2, so it is not specified. It is considered as 2 only.
Hello. Can we move on to the next part of the session?
Yes, Himanshini, you can take on.
Sure. Hello, everyone. Can you see the screen? Yes, there will be attendance for this part also. Okay. So my name is Hema. I'm going to take the second part of today's session, which is sorting. Okay. So we'll just have some overview on sorting, introduction. Then we'll just look at a few basic algorithms. We'll not go too much in detail of this because this is not that important for CP. And then we'll see inbuilt sort function, which we are going to use heavily in CP. So this part is important. And we will see custom sort, how we can make this function sort according to our needs, how we want to sort, like whether we want it in ascending or descending, etc. Okay, so moving ahead. Okay, so before we start Am I lagging? Okay, so the thing is that it's raining here, so I may lag. Please tell me if I do that. Okay? Yeah. So sorting. Sorting is a technique to put elements in a this with to into an order. So it can be ascending order, descending order, and it may not be numbers only. It can be letters. You can put letters in alphabetic order. You can put them in reverse alphabetic order, etc. So yeah. So a simple example is sorting elements in an array of numbers, integers. Yeah. So why should we sort? So let's say I give you a problem where I give you a random unsorted array and I ask you to find the second smallest element in that. So you can do that easily. You'll just do linear search, you'll find the smallest element, then you will ignore that element, and you'll find the smallest element except for that element. So that will be the second smallest element. Yeah, sure, you can do that without sorting. But let's say I give you an array of 100 elements and I tell you back to back. First, you have to find 37th smallest element, then you have to find 63rd smallest element, then you have to find 5th smallest element. Okay, now you can't do that directly by searching because that's too much. It will have high time complexity also. So, a really good way to go about this is to sort the array. So, can you sort? Let's say you have an array and you sort it. So the smallest element will have the index 0 since arrays start with index 0 till and go till n minus 1 when array is of length n. So the smallest element will have index 0, second smallest element will have index 1 and so on. So the question which I just told you can just do it easily by for 37th smallest element you will first sort the array and then output where the value where index is 36. For 67, you will do that for index 66. So you can solve like when many queries are given, you can solve such questions easily using sorting. And like there are many questions if you check on code forces which are not directly based on sorting, but you will need sorting in this. So it's an important concept. Moving on. Yeah, so these are some sorting algorithms. Like these are very basic bubble sort, insertion sort, selection sort. This you may have learned in school if you've taken CS. And then there's quick sort. So to be honest, this is not very important for CP. And by not very important for CP, I mean you will not use them in CP. Okay? Because there is a direct function which you can just put and it will give you sorted array in the fastest possible time. So we'll just look at the logic behind this. We will not go through this too much in detail. Okay? Is that fine with everyone? You can hear me, right? Okay. Moving ahead. So bubble sort. So what you do in bubble sort is first you have this given array initial which I have written here also. So you just check two elements at a time. If the first element is greater than the second element, then you swap those two elements. If it's not, you keep it as it is. And you go through each two elements continuously. So first I will check these two. These two are proper. They are the first one is smaller than the second one. So we'll keep it as it is. Over here, this 4 is greater than 2. So we should swap it. So here it is swapped. Now next two elements. This is okay. So we'll keep it. Next two. This we need to swap. So we'll swap it. So like this is after first iteration. So if you notice here, time complexity is n square. So it means you're doing this whole thing is one loop and you're doing this whole thing multiple times over here. So you do this and you finally get the sorted array at the end. Okay, is that fine? Yeah. So this is it has a high time complexity. It's not very efficient method, although it's easy to understand. So it's not going to be. Similarly, these two also, since we are a little bit short on time, we'll keep it in the slide. You can read about it later. We'll share the slides to you. So you just skip this for now. And yeah, quick sort. So this has less time complexity. n log n. And actually, n log n is the best time complexity for the sorting algorithm. Okay, so this is the best you can get. You cannot get it in lesser than that. Okay, so yeah. So what you do here is you choose an element, usually the last element, and then what you do is you just write code so that all the elements which are smaller than this last element are towards the left of it, and which are bigger than that are towards the right of it. Okay. So finally, when you do this, the element which you chose for your now it's the last element, so that comes in its correct position. Okay. Yeah. And then you treat these subarrays which are to the left of it and to the right of it as separate arrays, and you repeat the task. You again choose the last element of this part. You put the elements which are smaller than that to the left and larger than that to the right. And finally, you'll end up with a sorted array. So this is quick sort. Okay. Any doubts till now? This is not very important when it comes to CP. What comes next is important, but any doubts? Okay. Okay, so we'll move ahead. Now we come to the important part. Okay. Yeah. So inbuilt sort function. Okay. So in C++, you will have an sort function which you can directly use. You don't need to write an algorithm for sorting at all, especially in CP. Okay. So this is what it looks like. You can see over here, right? So it gives sorted array in minimum time complexity. So this sort function uses quick sort, heap sort, and insertion sort. Some weird combination of that. That's not that important for us, but it will give you the sorted array in fastest possible time. Okay. So how do we write this function? So while writing this function, we need to give at least two elements, or we can give three elements, three parameters. Sorry, two parameters or three parameters. So the first parameter will be addressed to the start of the array, and second will be to the end of the array. So if you see over here, we are having array of A, which has n integers. So we are going to give starting of the array, which will be A, and end of the array, which will be A plus n. So here you can see this is an array with 7 elements. So we'll start off giving the starting address, which will be here. You can assume this A to be like A plus 0, so element with I 0, and A plus 7. So this is last element will be, since the array has 7 elements, here I index will be 6. So after this, so this sort function sorts from starting till what comes just before the last thing which we give here. Okay, this points to the end of the array, like ending of the array. So like this, and third parameter is how you want to sort it. This part we will see later. It's the custom sort part. Okay, and yeah. So when you don't give this, like here, we have not given any extra thing. It sorts it in ascending order. Okay, so using this sort function, you can sort array of integers, like any array. You can sort strings also. Strings, they will sort according to ASCII values if you don't give anything. So characters, numbers, capital letters, small letters. So and the letters are in alphabetical order. So it is according to ASCII values, element letters. Okay, and we'll can also sort vectors. Vectors we can directly point using v dot begin to the beginning of vector and v dot end to the end of the vector. So we get it sorted. Okay, any doubts, anyone? Or can we move on? Or do you want me to repeat? Yeah, third parameter will come to it shortly. Just few slides, okay, just little bit. Yeah. Anything else? Or can we move on? Time complexity is n log n. The best time complexity you can get for a sorting function is n log n. So class is not yet over. Yeah. Okay, sure. So let's move ahead. Yeah, so this is an example code for using it. So we'll take in input of L. So I've given 10 here. We'll take in the array, which I have given here. And then we'll just output it before sorting once. So this is before sorting. And then this is without the third element. We are directly giving in the sort function. So sorting function, and then you get sorted array in ascending order. Okay. When you don't give anything, it will by default give in ascending. So next. Okay, so here's the question. You can answer it on Slido. Scan the QR. You can see the QR, right? So, okay, yeah. So answer the question. I'll just read it out once. Write the function such that it sorts array in ascending order between third element and eighth element. So you just need to write the sort part, okay? So it should sort. It should not sort the whole array. It should start sorting from the third element and up to the eighth element. Okay? Yes. Lots of confusion. Okay, so people are giving different answers. I have not told you the third index and the eighth index. I'm saying from third element to the eighth element. Third element to the eighth element. So give you 5 more seconds. You need to write a plus the number and comma a plus the number. You cannot directly write the numbers there. Okay, we'll see the answer. Yes, so as you can see, it will be from a plus 2 to a plus 8 because we are doing including the third element. Okay, so from index 2, I mentioned including the third element, right? Yeah. So from index 2, which is the third element, till here, before this. So you need to do a plus 2 and a plus 8. Is that fine? Right? Okay, so maximum answers that I got was 2 comma 7. So it, 7, it is right. We are sorting till element with index 7, but as I mentioned before, over here, we need to give the value which is 1 after that last element which we are sorting. So here, since we are sorting from I is equal to 2 to I is equal to 7, we have to give one number extra here. Okay. And many are giving from A is equal to, sorry, many are saying from A, many are saying 8 plus 3 comma A plus 8. So that's also not right because I said third element. Third element will have index 2. Is that fine? Yes. Why are we adding A? Because see, we are giving the address of the this thing, right? Uh, the whatever we are passing, we have to pass the address of the array inside the memory of the computer will be stored as consecutive in consecutive blocks. So A represents the starting element का address. Okay. So we're starting from there, and from there we are doing plus two places. So let's say this is a place which is denoted by A inside the computer. So A plus 2, 1, 2 from here. Okay, like that. Is that fine or yeah, it acts like a pointer to the first element. Okay, yeah. So, so from ith element to jth element, it will be like this. A plus I minus 1 because we are representing the index of the ith element. And A plus J will be actually A plus J minus 1 plus 1. So minus 1 because that index, and we have to show one more extra. So that it's from starting from this before it reaches this. Starting from this before it reaches this. Is that fine? That's why over here also we are doing A and A plus N. If it was like what you were saying, that from we should do till that much element only, then it would be A plus N minus 1. But it's not. Okay. We are taking one more element extra. So we have to, it's like we are starting from here and we have to stop before this. That's fine. That's fine. You can hear me, right? Guys? Okay, so now we'll go to sorting vector pair. Okay, so do you know what a vector pair is? Yes, no, yeah, so it wasn't covered in the previous section, so I'll just tell you what a vector pair is. Okay, so a vector pair will be defined like this. So you know what a vector is, right? So vector, and if you put like this and you just put int instead of this whole part, you just put int, then it's like an array, but it's a vector, and you will have the same functions that are like v dot begin, v dot end, and all those, which you have done in last class, right? So vector, this what this pair is that it associates two integers together, not necessarily two integers. It can be int, char double, int double, anything. Okay, but it associates two elements together. That's a pair, and a vector pair is a vector of these pairs. Okay, does that make sense? So it will look like this: vector pair int v of n, and then once you have this vector, this v of I, which you are like accessing each element of the vector. This each element will have two parts. We will have a first part and a second part. So first part, when we write, let's say v of 1, or let's take v of 0. V of 0 dot first, we are referring to this. And we write v of 0 dot second, we are referring to this. Okay, like this. V of I dot first, v of I dot second. Okay, so it's kind of like an array only, or kind of like a vector only, but it has two elements per slot. Okay, if that makes sense. Makes sense, right? Okay, do you have like a rough idea of what a vector pair is now, or should I explain it? Okay, you can hear me, right? Okay, yeah, I'll explain it. Yeah, so it's like ultimately like an array only, but in array, what happens? Each a of I will have only one value in it. Here, a of i's will have a pair of values. Okay, so In a vector, we take one element v of I. It will have only one element. Here, v of I itself is a pair. Okay. So in a pair there are two elements. So this v of I will have two elements. So this one whole thing is v of 0. This one whole thing is v of 1. This one whole thing is v of 2. This one whole thing is v of 3. Okay. Okay. And this each element we can access by writing, let's say for this one, we write v of 0 dot first. Okay, like this. V of I dot first. V of I dot second. So V of 0 dot second will give refers to this second element which is there here. Does that make sense? Okay. Got it again? Okay, you'll get it when we move on. So I'll continue. So now when you have a vector pair like this, okay, there are many ways you can sort it. You can sort it according to the first element. So just you don't look at the second elements of these pairs. You only look at the first element, and you can sort it according to this, or you can sort it according to the second elements of this. You can just not look at the first parts and only look at the second parts and sort it according to that. That also you can do, or you can first sort it according to first element in ascending order, and then you can sort it according to second element in ascending order. So like say 1, 1, 2, like 3, 6, and then these two are 3 are same, right? So yeah, wait, we will get it when we move in. Okay. So like there are many ways to sort this picture, right? Like but there is only normal and you can sort it ascending or descending. But this one you can sort ascending according to first element, ascending according to second element, ascending according to first element, etc. So we'll look how to do that. Okay. So what happens when we directly use the sort function here? So I have defined this vector pair. I have taken inputs and all for this, and this as written sort function as we had written it before. Okay, and I just outputted it after sorting. So this whole is the input part, and before sorting, it is like this. Okay, randomly it is given, and after sorting, without like giving any preference, it gets sorted according to first element. First elements, if you see, are in ascending order. Okay, and besides the first element, after when the first elements are the same, the second elements are in ascending. Same. Here 3, 3, 3, and the second elements are in ascending. 1, 2, 6. There are also 4, 4. When these are same, the second elements are in ascending. 3, 5. And see, while giving, I'm not given it like this. It became in ascending. So when you use the sort function directly on this, without giving any preferences, you will get it in first priority, first element is in a second ascending order, and second priority, the second element. Okay, you get it. You get it right? Like just the logic. This is when you don't use any specific way for something. So this is like the default way. So now how to customize? So I was talking about the third element, right? So this is it. Okay, the third input you're going to put in this. So this will be a function which you define above your code. So it will be looking like this. Boolean. Okay. Boolean, which means it will return value either true or false. Custom sort. This one is for a normal array only. Okay. So before we did this, it used to sort when we did not give this anything. It used to sort in ascending order by default. But we can customize it however we want. So here I have given bool custom sort int a, int b. Okay, so it should have two integers input or two inputs of whatever this of that type. Okay, and we will return A greater than B, which means this is for correct A should be greater than B. So accordingly, this will return true false. Accordingly, this function will read, and accordingly, since this is A should be greater than B, you will get it in descending order. Is that fine? This is how you are supposed to write the function. Okay, got it right? Or should I repeat? Right? Okay, I'll repeat. Yeah. So this is how you write a custom sort function. So that you can sort however you want. So this is for an array, okay? Not for a vector array. This is for a normal array. So you take two inputs, you write a function like this, okay? This name can be anything. So this has to be a Boolean function. So that it returns either true or false. Okay? So this should have input of two of the type of this array, like whatever type it is, here it is integer array. So two int values I'm passing to it, A and B. Okay? And then we will return A greater than B. What we are doing is we are manipulating this sort function to give us a descending order of sorting. Okay, so A greater than B. So look here, finally we got the array sorted in descending order. So this will return some true when it is true, false when it is false, and accordingly the sort function will take care of it and will get sorted array in descending order. Okay, if we put A less than B here, then we would get it in what order? If you put A less than B. Can you hear me? Hello? Can you hear me? Someone said no sound. Okay. Yes, you can hear me. So if I put A less than B over here instead of A greater than B, how will the array be sorted? In ascending order or in descending order? Okay, ascending, right. Good. So like this, the same function we will use to manipulate vector pairs also. Okay. So here, when you're taking vector pair, you're going to take pair each time inside. Okay. So it will be pair int int A, B. And then you will sort A dot first greater than B dot first. So what we are doing here is we are sorting it such that element A, the first element of A is greater than first element of B. So typically what we are doing is we are sorting first elements in descending order. Okay. And second elements are left as it is. Can you hear me? Because my light just went. Can you hear me? Can you hear me? Okay, you can hear me, right? My light just went. I got it. Yeah. Sorry. Yeah. So given a vector pair which has intent, okay, two integers, you can sort it according to the first integer by doing something like this. If instead of putting A dot first and B dot first, if I put A dot second and B dot second over here, okay, what do you think will happen? Instead of putting A dot first and B dot first, I put A dot second and B dot second. according to what will it get sorted? Will it be in ascending order to first attendance will be taken later. Ascending order to first element, descending order to first element, descending order by, yeah, correct, descending order by second element. Okay. Do I need to repeat or is everyone understanding?
తిరుపతి లడ్డు రేట్ ఎంత ఏమవుతుంది నేను
Ascending by
ఎలాగన్నా
second,
రేట్
yes, correct.
రేట్ రేట్ తిన్నదే కదా
Okay, so guess what this function does? Let's see if you can. Attendance link you'll get at the end of the this function, guys. Okay, which one has the preference? This one or this one? Like, what will it see first? Whether what should we consider first? Whether first element should be greater than second, descending by first, right? And then if first elements are equal, then what will happen? It is descending by first, that is right. If the two first elements are equal, then what will happen? Yes, ascending by second if first is same. So what we are doing here is we are checking whether first is same first. So if A first is equal to B first, then second element should be A first. A dot second should be less than B dot second. Otherwise, if these are not equal, then A dot first greater than B dot first. So you can see here the first element is in descending order, and wherever the first element is the same, like there, then the second element is in ascending order. Okay, so this is something which is very useful in CP. So I hope you all. Okay, so here's a question for you guys. You can. What should come in the place of P and Q so that you get this output finally? So you see how the output is first. What is ascending? What is descending? And what should come in the place of P and Q? I've opened the poll on Slido. You can vote there. Is the screen lagging for everyone? Also read properly here. Given not equal to, whereas previously said given
ఎంత
equal
ఉందన్న
to.
కుదరనే అవుతుంది దగ్గర ఈ దగ్గర రారా ఆడుతుంటారు అయితే ఏం చక్రాలు హీరో దగ్గర
Okay. So as you can see here, the second elements are in descending order. And here I've given if second A is not equal to second B. So this is the case where they are not equal. So in that case, second B should be greater than second A should be greater than second B. Right? So that it is in descending order. And in the case where they are equal, then we are sorting the first elements in ascending orders. So here it should be less than. So answer is first greater than and then less than. Okay, is that fine? Yeah, so finally I'll give you guys your attendance. You can scan it and also please give feedback. Also, you can ask doubts if you have in the chat or if you want me to repeat everything, especially the vector pair part. And yeah, session is over, but like I'm still taking in any doubts if you have. Ah, we call it above outside the main function. The Boolean function which is there, right? We will be having this main function here on top over here outside the main function. You call that. Okay? Like you will have hash include IOStream, then using namespace std if you want, and then here you call your Boolean function outside it, and then you call the main function. Is that fine? And then you call it in the it is passed as a third parameter to the sort function. Attendance link. Okay, attendance link. Very important. Also, guys, please feel feedback. It helps a lot. Attendance link is not opening. Even. And then this is the link that I was given. Maybe it's the same one as the previous one. Okay, yeah. So that's it for today. If you have any doubts, please ask. Guys, if you are like having any doubts, especially in vector pairs, you can please ask. I know it was a little oh, technical. Oh, thank you. Yeah, you can leave. Can we add both adapters? If you registered for both, I think, and have 80% attendance in both, you will yes, get certificate for both. Yeah, that comes in code. Okay, so I guess we should end the session today. There are no more doubts on vector fields and sorting. Yeah. Have a great day. Good night, guys. Good evening.